Now we will discuss about the signal system, subject of principle of communication engineering. Classification of signal and systems. So what is the signal and system in the communication system engineering? So a signal is a pattern of variation that carry information. Signals are represented mathematically as a function of one or more independent variables. A picture is brightness as a function of two spatial variables x and y. So in this course, signals involving a single independent variable generally referred to as a time. T are considered, although it may not represent a time in a specific application. A signal is a real value or scalar value function of a independent variable t. So signal may be real value or it may be scalar value function of independent variable t. There are some signal examples. First one is electrical signal. So what is the electrical signal? Electrical signals voltage and current in a circuit, that is the electrical signal. Acoustic signal, audio or speech signals, analog or it may be digital, that is the acoustic signals. And video signals, intensity variation in an image, or for example, a cat or a city scale. Biological signals, that is the sequence of base in a genes, and also a noise signal, unwanted signal. So there are different examples of signals, and these signals also we can see in this figure in the different form. Measuring signal. So in the signals, we can measure of this signal the amplitude and time period in the form of amplitude. We can measure amplitude in the form of voltage or current, and we can measure of period in the form of time and frequency. So this is the measuring signal diagram, which is in the form of sinusoidal. There are different definitions about what is the voltage. So voltage, the force which move an electrical current against resistance. So that is the voltage. And waveform, what is the waveform? The shape of the signal previous slide is a sine wave derived from its amplitude and frequency over a fixed time. Other waveform is a square wave, triangular wave, or maybe cosine wave. And what is the amplitude? The maximum value of a signal measured from its average state. And what is the frequency of pitch? The number of cycles produced in a second hertz. Relate this to the speed of a processor For example, 1.4 gigahertz or 1.4 billion cycle per second. So this is the definition of frequency. What is the signal basics? So continuous time CT and discrete time DT signals. So these are the two forms of the signals. The continuous time CT signal take on real or complex value as a function of an independent variable that range over the real numbers and are denoted as xt. In discrete time signal, DT signal are take on real or complex value as a function of an independent variable that range over the integers and are denoted as a xn, where n is the integers. Note that the parenthesis and square brackets to between CT and DT signal differentiate as we can see these both signal in the form of waveform. So first is the CT signals and second so the discrete time signal. So first continuous time CT signal is the example of analog signal and the discrete time DT signal is the example of digital signals. So these are the representation of analog signal and digital signal in the form of continuous and discrete time signals. In analog signals, so what is the analog signal? Human voice best example of the analog signals. Ear recognized sounds 20 kilohertz or less. This is also example of analog signal. AM radio, which is have the frequency 535 kilohertz to 1605 kilohertz. And in the FM radio or frequency modulation radio, the frequency range is the 88 megahertz to 100 megahertz. So these are the examples of analog signals. And also there is others examples of signals which are we can see on these diagrams. There is example of time, temperature. Next one is digital signal. So digital signal represented by a square wave and all data represented by a binary values in digital signals. Signal binary digits, that is a bit, and a binary digit, that is the bit. Transmission of a group of bit is a bit stream. So not all decimal value can be represented by binary. So the binary digit are 0 and 1 in the form of 0 and 1. These are the bits, binary bits. What is the analog versus digital? So analog have the advantage in this signals best suited for audio and video. And second one, advantage of analog signal, it consumes less bandwidth. Next advantage is available worldwide. And next advantage of analog signal is the less susceptible to noise. So these are the some advantages of the analog signals. What we have in digital signals, there are also some advantage of digital signals. One is digital signal is best for computer data, and second, it can be easily compressed, and third, can be encrypted, and fourth one is equipment is more common and less expensive. This is the also disadvantage of digital signal, and also digital signal can provide better clarity. So these are the some advantages of the digital signals. What is the analog message? Analog message continuous in amplitude and over time. AM, FM for voice sounds. Traditional TV for analog video. First generation cellular phone analog mode. And next one is record players. What in digital message 0 or 1 or discrete values. So in VCD, DVD, 2G, 3G cellular phones, and also digital message and data on your disk, your grade, and digital age, why digital communication will prevail. Next, what is the analog to digital conversion and digital to analog conversion of a signals? Analog to digital to analog conversion, gateway from the communication device to the channels. Nyquist sampling theorem. Nyquist sampling theorem. This is the theorem. In this sampling theorem, from time domain, if the highest frequency in the signal is V Hertz, the signal can be reconstructed from its samples taken at a rate not less than 2V samples per second. So this is the statement of the Nyquist sampling theorem. Also, signal a function of one or more variable that convey information on the nature of physically phenomena. For example, VT, IT, XT, heartbeat, blood pressure, temperature, vibration, these are the examples of signals. One-dimensional signals. In one-dimensional signals, function depend on a single variable. For example, speech signal. This is the example of one-dimensional signals in which function depend on a single variable. So here the example, that is the speech signals. In multi-dimensional signals, the function depend on two or more variable. For example, the image signals. So image signal is the example of the multi-dimensional signals in which function depend on two or more variables. So these are the some examples of one-dimensional signals and multi-dimensional signals. There are also different signals, and we can classify the signal into different form. So it may be in continuous time and discrete time signals, periodic and non-periodic signals, casual and non-casual signals, deterministic and random signal, and even or odd signals. So these are the different classification of the signals. Continuous time CT and discrete time DT signals. So CT signals takes on real or complex value as a function of an independent variable that range over the real number and are denoted by xt, and dt signal take on real or complex value as a function of an independent variable that range over the integer and are denoted by xn. So these are the two waveforms of the ct and dt signals. Next one is the periodic and non-periodic signals. In periodic signals have the property that x t plus capital T equal to xt for all t. This is the property of the periodic signals. The smallest value of t, capital T, that satisfy the definition is called the period of the signal. Shown below are n non-periodic signals left and a periodic signal is right. So in this diagram, a non-periodic signal and a periodic signals are represented here. Next one signal is casual or non-casual signals. A casual signal is 0 for t is less than 0, and a non-casual signal is 0 for t is greater than 0. So this is the casual signal. It may be represented in this diagram waveforms. Right and left sided signals. So in this given two diagrams of right and left signals, a right side signals is 0 for t is less than capital T, and a left side signal is 0 for t is greater than capital T, where capital T can be positive or negative. And also we can see this in this two waveform diagrams, which is the function of xt and t. And next one is the deterministic and random signals. So in these signals, behavior of these signal is predictable with respect to time. There is no uncertainty with respect to its value at any time, and these signal can be expressed mathematically also. For example, xt equal to sine 3t is deterministic signals, and also this signal is represented in this diagram by the waveforms. Waveforms is continuous waveform and also in form of discrete form. Random signals, the random signals is as shown we can see in this diagram. Behavior of these signal is random, not predictable with respect to time. There is an uncertainty with respect to its value at any time. So these signals can't be expressed mathematically. So random signals can't be expressed mathematically. For example, thermal noise generated in non-deterministic signals. So thermal noise is, we can see thermal noise as in this graphical diagram, waveform, in this waveform diagram. Next, even and odd signals. So what is the even and what is the odd signals? Even signals X, ET and odd signal X, OT are defined as, so even signal X, ET equal to X, E minus T and X naught T equal to minus X naught minus T. So these are the even or odd signal, can be written by in this form. Any signal is a sum of unique, odd and even signals using xt equal to xet plus x naught t. This is the sum of odd and even signal. And x minus t equal to xet minus x naught t. And also xet equal to 0.5 in bracket xt plus x minus t and x naught t equal to 0.5 into xt minus x minus t. So these are the even and odd signals. So for even signals, if x minus t equal to xt and x minus n equal to xn. So these are the even signal. What in odd signal, x minus t equal to minus xt and x minus n equal to minus n minus xn. This is the example of odd signals. Any signal xt can be expressed as xt equal to xet plus xot and also x minus t equal to xet minus xot, where xet equal to 1 upon 2 into xt plus x minus t and also x naught t equal to 1 upon t into xt minus x minus t. So these are the even and odd signals examples. What is the bounded and unbounded signals? Every system is bounded, but meaningful signal is always bounded. So bounded and unbounded signals, here in this graph representation, there is the first graph xt versus time, and second also xt versus time. So there is unbounded and bounded signal represented for casual, and in second graph for anti-casual, unbounded and bounded signal also represented in the different quadrants of these graphs. Next, what is the power and energy signals? Power signals infinite duration. Normalized power is finite and non-zero. And power signal normalized energy average over infinite time is infinite, and also power signal mathematically tractable. What in energy signals? The energy signal finite duration, have the finite duration, and have normalized energy is finite and non-zero, and also energy signal normalized power average over infinite time is zero, and also energy signal have physically realizable. There are some elementary signals. So step functions, impulse function, and ramp functions, these are the examples of elementary signals. And what is the unit step function? So we represented the unit function by the ut. So what is the ut equal to 1 in continuous time signal if t is greater than 0, and ut equal to 0 if t is less than 0. These are the two conditions and for the unit step function in the continuous time signal, and also the unit step function in the discrete time signals, and can be represented by the un, and the value of un equal to 1 if n is greater than or equal to 0, and second condition un will be equal to 0 if the value of n is less than 0. So this is the unit function in different continuous and discrete time signals forms. Next one is the unit impulse function. So unit impulse function can be represented by the delta t. So we can represent unit impulse function in continuous time signals form and discrete time signals form. In CT signals form, delta t will be equal to 0 if t is not equal to 0, and delta t will be equal minus infinite to infinite delta t dt, or equal to minus 0 to 0 integration delta t dt equal to 1. So these are the two conditions in CT signals. What in discrete time signal? The unit impulse function represented by the delta n. So delta n will be equal 1 when n equal to 0, and delta n equal to 0 when n equal to not 0. So these are the impulse functions. Next one is unit ramp functions. So RT equal to T when T is greater than 0, and RT equal to 0 when T is greater than 0. So this is the unit ramp functions. And also RT equal to T ut, And also we know ut will be d upon dt rt. So equal to dt d upon dt into r equal to 1, and rn equal to n if n is greater than 0, or rn equal to 0 when n is less than 0. Next, what is a system? So system process input signal to produce output signal. This is the systems in which input signals to produce a output signals. For examples, a circuit involve a capacitor can be viewed as a system that transforms the source voltage or signal to the voltage signal across the capacitor. And second example, a CD player take the signals on the CD and transform it into a signal sent to the loudspeaker. So this is the second example of the system. Also, third example, a communication system is generally composed of three subsystems. First, the transmitter, the channel, and receiver. So these are the three subsystems: transmitter, receiver, and channels. The channel typically attenuate and add noise to the transmitted signals, which must be processed by the receiver. So these are the some examples of the systems. How is a system represented? A system takes a signal as an input and transforms it into another signal. In this diagram, a input signal is the xt, and a system transfer to the this input signal to the output signal in the form of yt. So in this diagram, a system transfer the input signal to the output signals. In a very broad sense, a system can be represented as the ratio of the output signal over the input signal. So this is the system representation. That way, when we multiply the system by the input signal, we get the output signals. This concept will be firmed up in the coming type of systems. There are different systems. First one is casual or non-casual system, linear and non-linear system, time variant and time invariant system, stable and unstable system, static and dynamic system. So these are the some types of systems. So what is the casual system? A casual system is said to be casual if the present value of the output signal depend only on the present and or past value of the input signal. So this is the casual system. For example, yn equal to xn plus 1 by 2 xn minus 1. This is the example of casual systems. Non-casual system. In non-casual system, a system is said to be anti-casual if the present value of the output signal depend only on the future value of the input signal. So that is the non-casual system. For example, yn equal to xn plus 1 upon 2 into xn minus 1. This is the example of non-casual systems. And what is the linear and non-linear systems? In linear and non-linear systems, a system is said to be linear if it satisfies the principle of superposition. For checking the linearity of the given systems, firstly we check the response due to linear combination of inputs. Then we combine the two outputs linearly in the same manner as the inputs are combined, and again total response. Check response in step 2 and step 3 are the same. The system is linear, otherwise it is non-linear. So this is the concept of linear or non-linear systems. Next one is time invariant and time variant system. A system is said to be time invariant if a time delay or time advance of the input signal leads to a identical time shift in the output signals. For example, yt equal to h into xt minus t naught, and also h s t naught xt equal to h s t naught xt, and y naught t equal to s t naught yt, and also y naught t equal to s t naught h xt and equal to s t naught h xt. Next, linear time invariant system, LTI systems. A special importance for their mathematically the most signal processing application involve LTI systems. So LTI system can be completely characterized by their impulse response. So for linearity, yt equal to t in bracket xn equal to t summation k from infinity to infinity xa into delta n minus k, and time invariant k summation of k from infinity to infinity xat into delta n minus k equal to summation of k minus infinity to infinity xk hk and t time invariant. So summation of k equal to minus infinity to infinity x k h n minus k equal to x k into h k. Stable and unstable system. A system is said to be bounded input, bounded output, stable if every bounded input result in a bounded output. The example of stable and unstable system, the system represented by yt equal to axt is unstable if a greater than 1. Reasons, let us assume xt equal to ut, then at every instant ut will keep on multiplying with a and hence it will not be bounded. static system, in static system is merely memoryless system. So static system is the memoryless systems. It has no storage device and its output signal depend on present values of input signals. For example, IT equal to current 1 upon R Vt. This is the Ohm's law. And dynamic systems, a dynamic system possesses memory. It has the storage devices, and a system is said to possess memory if its output signal depend on past value and future value of the input signal. So IT current equal to 1 upon L integration of minus infinity to T Vt d tau. So Yn equal to xn plus xn minus 1. This is the example of dynamic systems. Memoryless system. What is the memoryless system? In memoryless system, a system is memoryless if the output Yn at every value of n depend only on the input xn at the same value of n. For example, square Yn equal to xn a whole square, and also sine Yn equal to sine xn. So counter example, ideal delay systems, Yn equal to xn minus n. And now discrete time systems. In discrete time, sequence is a mathematical operation that maps a given input sequence xn into an output sequence yn. Example of discrete time system: moving running average yn equal to t xn. So xn thanks to t or thanks to yn. Yn equal to xn plus xn minus 1 plus xn minus 2 plus xn minus 3. The maximum yn equal to maximum xn into xn minus 1 and xn minus 2. In ideal delay system, yn will be equal to xn minus n. There are some system properties. So here H is represented the system. In this system, xt is the input signal and yt is the output signal. So H represented the signal xt, yt represented a system with input xt and output yt. Stability, bounded input, bounded output stability. So xt modulus of xt less than equal to mx or less than infinite equal to modulus of yt less than my less than n infinite. Modulus of xn less than equal to mx less than infinite, and also equal to yn modulus of yn less than m by dash less than infinite. So memory system present output value depend on future or past input. So memoryless system present output value depend only on present inputs. For example, memory systems yt equal to 5xt plus integration minus infinity to t xt dt, and yn equal to summation of n minus 5 to n plus 5 xn. So memoryless system yn equal to xn plus x square n. So these are the two examples of memory system and memoryless systems. Casual present output depend on present past value of the inputs. Non-casual system present output depend on future value of input. Note memory less equal to casual, but casual not necessary to be memory less. It should be noted. Time invariance, TI, time delay or advance of input, and identical time shift in the output. Let us define a system mapping yt equal to hxt. The system is time invariant if xt minus t naught equal to y t minus t naught. Also x n minus n naught tends to y n minus n naught. And linear system if x1t tends to y1t and x2t tends to y2t, then ax1t plus bx2t tends to ay1t plus by2t, else nonlinear. So properties of a system. On this course, we shall be particularly interested in signal with certain properties. A casual system is casual if the output at a time only depend on the input value up to that time. And linear system is a linear if the output of the scaled sum of two input signal is the equivalent scaled sum of the outputs. Time invariance, a system is time invariant if the system output is the same given the same input signal regardless of time. These properties define a large class of useful system and will be further considered in the coming lectures. So these are the some reference books. Digital Communication by the Simon Hackens. Second books, Principle of Communication by the Topsily. And there are some multi-choice questions. Thank you. Thank you very much.